Okay, so for a Mealy type finite state machine, so let us use the same input sequence. So let's say for W, so we have input sequence 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1. So we have here a clock, with clock 0, 1, 2, 3, 4, 5, 6, 7, 9, 10. Then we have the output K. So for a Mealy type FSM, for this input sequence, so if the machine detects two consecutive input of 1, 1, so it will assert the system, or it will output a 1. So this time at the same clock cycle of the next input. So here we have 1, 1. So the output will be the same clock cycle of this input. So this is 1. Another input sequence 1, 1. So this output is a 1. So output 0, 0, 0, 0, 0, 0, 0, 0. So for the Mealy type FSM, so you can use the number of input sequence is equals to the number of states. So let's say state A, or at state A, so let's say we have input 0, output is 0. So at state A, so let's say W is 0, so its output K is equals to 0. So at state A, it will input 1, so it will move to the next state, B. So again, for the Mealy type FSM, so I use the number of input sequence is equals to the number of states. So we have 2 input sequence 1, 1. So the number of states, so we have A and B. So 2 states. So here we input W is equals to 1. So its output K is equals to 0. So at state B, if I input 0, so it will move back to state A. So W is equals to 0, so its output K is equals to 0. So here I have input 1. So I input 1 at state B. So its output is K is equals to 1. So at state B accepts K is equals to 1. So we're going to use this state table or state machine to draw our state table. So we have our present states A and B. Then for the next state, so we have input W is equals to 0, W is equals to 1. Then for the output K, so we have input W is equals to 0, W is equals to 1. So this is our state table. So A input 0, so state A. So A input 1, so we'll move to state B. So this output 0, this is output 0. So state B input 0, so we'll move to state A. This gives output 0. State B input 1, so it will stay at state B. This gives an output 1. So using this state table, So this is our state table. So we're going to generate our state assigned. So we assign A is equals to 0 and B is equals to 1. So again, for our present state, so let us use the variable y to hold 0 for A and 1 for B. So for the next state, so we have W is equals to 0, W is equals to 1 input. So we have state y. Then for the output, K, we have W0, input W1. So this is A is 0, A again is 0, B is 1, so this is 1, 1, 0, 0, 0, 1. So let us implement. So again, this is our state assigned table. So let us implement the circuit using D flip-flop. Okay, so for D flip-flop, so we have D is equals to next state. So our next state is 0, 0, 1, 1. So therefore, our flip-flop inputs. So for W is equals to 0, W is equals to 1. So we have D, Y. Here we have D, Y. So we have 0, 0, 1, 1. Okay? So let us derive our expression for D, Y. So we have here W, Y, 0, 1, 0, 1. So W equals to 0, so 0, 0, 0, 0. For inputs equals to 1, so dy is 1, 1. So therefore, dy equals to the input W. Then for the output, K, so we have here W and Y, so 0, 0, 0, 1. So therefore K is W, Y. So using this expression, we're going to draw our circuit for a Mealy type FSM. So we have one D flip-flop, dy. So we have here our clock. So this is our reset or clear. So for input dy, so we have here W. Then for the output K, so this is Y naught. So this is output K. So for the module, so let's say module Mealy FSM. So we have our clear end, clock, input W, state Y, and output K. So we have input, clear end, clock, and input W. Then for the output, we have the output for the state Y, then another output for K. So this one is simple. So we're going to use our previous example for DFF E. So we connect clear N with clear N, connect the clock with the system clock, then we connect input D of our flip-flop to, so input is W, then we connect our state Q of our flip-flop to Y. Then for output K, so we use the sign keyword, that is W and with, so this is Y state, then N module. So for the synthesis, using Synchronous, so I have implemented a while ago. So here is our module for our flip-flop. So here's our expression. So you can change this name for Mealy. So this one I used for our previous example. So that is DFE. So let's say this is int1. Okay, so input is W, then state Y. And output K is W and with Y. So let us synthesize. So I have already created a test bench. So again, this is for a Mealy. So you can change the name for as Mealy FSM. Then for same input sequence, so we have 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1. Okay, so let's simulate some behavioral model. So now this is our output. So let us see if the same is true. Okay, so for synthesis, so here we have sequence W is equals to 1, W is equals to 1. So again, on the same clock cycle, so the output K is equals to 1. So 1, 1, output K is 1. So here we have 1, 1 again, so the output K, so on the same clock cycle, K is equals to 1, so 1, 1 again, so same clock cycle, K is equals to 1. So that is all for circuit implementation and synthesis for a Mealy state machine or Mealy type FSM.